dilated matter. And that's a really evocative way to approach some truly fascinating areas of physics where matter behaves, well, in ways we don't normally see. It's a perfect launching point for a deep dive.
Absolutely. That idea of dilation, even, without a strict textbook definition, it immediately brings to mind several realms where matter undergoes pretty significant changes due to extreme conditions. It really highlights how a curious question can lead us to some profound insights about the universe.
Okay, so when we started unpacking this idea of dilated matter based on the material you flag, a few key themes emerged. We're looking at everything from the fundamental expansion of the cosmos and its effect on light, to the everyday phenomenon of materials expanding with heat, and even the incredibly energetic state of matter in particle accelerators. Our mission here is to explore these connected ideas and see what surprising insights emerge.
Right. So let's start with cosmological expansion. The universe itself is expanding, and a key piece of evidence for this is the redshift of light from distant galaxies. Their wavelengths are stretched as the space they travel through expands. Now, a crucial point here is that the matter within that space isn't growing in size because of this expansion.
Exactly. It's the underlying fabric of space-time that's stretching, not necessarily the galaxies and stars embedded within it. Then we considered thermal expansion, something, we encounter all the time. Think about a bridge lengthening on a hot day. That's just atoms jiggling more intensely and requiring more space.
Precisely. Increased temperature equates to greater kinetic energy at the atomic level, leading to increased separation between atoms and a resulting macroscopic expansion of the material. While it's a lower energy form of dilation compared to what we'll discuss later, it's vital for practical engineering, obviously.
And then we get to the really extreme end of the spectrum, with quark-gluon plasma. This is where matter is under such incredible heat and pressure that even protons and neutrons dissolve into their fundamental components, quarks and gluons, right? It's like matter stripped down to its bare essentials.
That's a great way to put it, a fundamental deconfinement. In these incredibly energetic environments, the normal structures just break down and these fundamental particles become free. This state existed in the very, very early universe and can be fleetingly recreated in particle colliders.
Now, this brings us to what feels like the core of the dilated matter concept, at least as I initially sort of envisioned it. Relativistic effects. When objects approach the speed of light or exist in extremely strong gravitational fields, their behavior deviates wildly from our everyday experiences.
hmm And what's truly fascinating is how Einstein's theory of relativity shows the deep interconnectedness of space, time, and matter. While relativistic dilated matter isn't a standard term, it's a compelling way to think about the unusual effects we see, such as, relativistic mass increase, length contraction, and time dilation, all impacting matter's behavior.
Okay, let's really dig into relativistic mass increase then. It's pretty counterintuitive that an object's mass would increase simply by moving faster.
It is, but it's a direct consequence of special relativity's core idea that energy and mass are equivalent, EMC. As an object gains kinetic energy and its velocity approaches the speed of light, that added energy actually manifests as an increase in its mass. The equation m equals m divided by the square root of 1 minus v squared over c squared that mathematically describes this relationship.
Okay, let's unpack that equation. M is the relativistic mass, m is the rest mass, v is the velocity, and c is the speed of light. So as m gets incredibly close to c, the denominator of that fraction, it gets very, very small.
Precisely. And when you divide by a number approaching zero, the result becomes increasingly large, approaches infinity. Thus, as an object's velocity approaches the speed of light, its relativistic mass approaches infinity.
Which is why our sources emphasize the absolutely enormous energy requirements to accelerate any object with mass to near light speed. It's practically an insurmountable barrier. Only massless particles, like photons, naturally travel at the speed of light.
Right. And this isn't just abstract theory. In particle accelerators, for instance, engineers have to precisely calibrate magnet strengths to account for the increasing mass of particles as they approach their target energies. Otherwise, the particles just wouldn't follow the intended paths. It's a real-world engineering challenge.
It's a great concrete example. Now, what about length contraction? If mass increases, do things also kind of compress in their direction of motion?
That's correct. From the perspective of a stationary observer, an object moving at relativistic speeds will appear shorter along the axis of its motion. The equation L equals L times the square root of 1 minus v squared over c squared quantifies this, where L rho is the object's proper length, its length at rest, and L is the observed contracted length. Interestingly, the moving observer wouldn't perceive this contraction in their own frame of reference.
So it's not just a visual illusion. There's a real physical contraction relative to that stationary frame. It's yeah, a mind-bending concept. And then there's time dilation, the idea that time itself slows down for objects moving at relativistic speeds relative to a stationary observer.
Indeed. For a high-velocity observer, time literally passes more slowly compared to someone at rest. A classic illustration is the behavior of muons. These are unstable particles, very short lifespan. However, when they're created in the upper atmosphere by cosmic rays and travel towards Earth at near light speed, they survive far longer than their intrinsic lifespan would suggest. Why? Because their internal clocks are running slower due to their high velocity. It's a direct, measurable consequence of time dilation.
Wow. So all these relativistic phenomena, mass increase, length contraction, time dilation, they're intrinsically linked and become really significant as we approach that ultimate cosmic speed limit. It's as if the universe has a built-in governor with some truly bizarre consequences for anything nearing it.
Precisely. And this brings us nicely to the idea of relativistic plasma, which your sources highlighted in astrophysical contexts. Consider the jets of particles emanating from quasars and black holes. These are often propelled at speeds very, very close to that of light.
So these aren't just ordinary clouds of gas then. They're matter in an extremely energetic state, exhibiting these extreme energy-momentum relationships precisely because of their near light-speed velocities.
Exactly. Now let's push this thought experiment further, as your initial questions seem to hint. What if mass were to somehow approach infinity at the very heart of a galaxy, at its central core? What kind of cosmic chain reaction might that trigger?
Okay, let's consider that. I mean, most galactic cores already host supermassive black holes. So if the mass there were to increase without any limit, the most immediate consequence would be just an absolutely overwhelming gravitational pull.
Correct. An unbounded increase in mass at a galactic core would almost certainly lead to a gravitational collapse into a singularity, a point of infinite density. It's essentially the ultimate runaway black hole scenario.
And if the mass of this central object keeps growing, what would happen to its event horizon, that point beyond which nothing can escape?
Yeah. Ugh. The Schwarzschild radius, which defines the event horizon of a non-rotating black hole, is directly proportional to its mass. So therefore, as the mass increased, the event horizon would expand correspondingly, engulfing an ever larger region of space.
And anything venturing too close to this infinitely massive object would experience some incredibly intense gravitational forces, right? Our sources mentioned the rather vivid term spaghettification.
Yes, they did. The tidal forces, which are the differences in gravitational pull across an object, would become so extreme that anything falling in would be stretched along the direction of the gravitational pull and squeezed perpendicular to it.
Yeah.
Resembling a strand of spaghetti.
Ouch.
Yeah.
A pleasant way to go. And what about the surrounding material in the galaxy? The stars, gas clouds, dust?
They would likely be inexorably drawn inwards by the immense gravitational well, forming a vast accretion disk spiraling into the black hole. As this matter accelerates and heats up due to friction and gravitational compression, it would emit tremendous amounts of radiation, potentially powering those high-energy jets we discussed earlier, but on a truly colossal scale.
So this hypothetical scenario of infinite mass at a galactic core could fundamentally reshape the entire galaxy, disrupting star formation, destabilizing orbits. It paints a picture of extreme cosmic upheaval.
It does. However, it's really crucial to revisit the fundamental limits our sources highlighted. Infinite mass is not physically achievable. The energy required to accelerate any massive object to the speed of light, let alone beyond it in some hypothetical mass-increasing scenario, becomes infinite. Relativity imposes these fundamental constraints on the universe's behavior. You just can't get there.
Right, so it's a fascinating thought experiment, but reality has its boundaries. But this whole idea of extreme mass and gravity at galactic cores naturally makes me think about the other major gravitational player on cosmic scales: dark matter. Could this mysterious invisible component of the universe be linked in some way to these central behemoths?
This is where the conversation takes a particularly interesting turn, and where current research is actively exploring potential connections. The relationship between black holes, especially supermassive ones at galactic centers, and dark matter is a very active area of investigation in astrophysics. Your sources touched upon some compelling ideas here.
Such as the hypothesis that some fraction of dark matter might actually consist of primordial black holes, tiny black holes that formed in the very early universe.
Exactly. These hypothetical black holes would be much smaller than the supermassive variety we see in galactic cores today. But if they were numerous enough, their sheer numbers could potentially contribute significantly to the overall dark matter density of the universe. It's a possibility.
And then there's the idea that dark matter might actually cluster around supermassive black holes, forming dense spikes that could have observable effects, maybe on gravitational waves or something.
Yes, exactly. Some theoretical models suggest that the intense gravitational fields of supermassive black holes could attract and concentrate dark matter particles in their vicinity, creating these high-density halos or spikes. These dark matter concentrations could then subtly alter the gravitational waves emitted during black hole mergers, for example, providing a potential way to indirectly detect dark matter. They might even affect the shadows of black holes as observed by the Event Horizon Telescope.
That's incredible. So the invisible presence of dark matter might be subtly influencing how we perceive and understand these cosmic giants. Our sources also mention the intriguing possibility of ultralight dark matter playing a role in the initial formation of supermassive black holes in the early universe.
That's another fascinating avenue of research. Certain theories propose that specific types of ultralight dark matter particles, perhaps with unique quantum properties, could have created the initial gravitational seeds or provided a mechanism for the rapid accretion of normal matter needed to form the supermassive black holes we observe so early in cosmic history.
So while there's no definitive answer yet, there's a growing body of evidence and theoretical work suggesting a real interplay between black holes and dark matter, and that studying these interactions might be key to unraveling the mysteries of both. It's not just separate phenomena.
Precisely. If dark matter does indeed interact with black holes in these ways, it could have profound implications for our understanding of galaxy formation, the evolution of black holes themselves, and the signals we hope to detect with next-generation gravitational wave observatories. It's a very dynamic field right now.
This is all so mind-expanding. Let's just take a step back for a second and revisit the fundamental characteristics of dark matter itself, just to really appreciate why this potential link to galactic cores is so significant. It's this non-luminous, non-interactive stuff that we only know exists because of its gravitational influence, correct? That's the whole mystery.
That's the central puzzle, yes. Dark matter doesn't interact with light or any other form of electromagnetic radiation, which makes it completely invisible to direct observation with telescopes. Its existence is inferred solely through its gravitational effects on ordinary matter, things like the anomalous rotation curves of galaxies, the gravitational lensing of light around galaxy clusters, and the overall large-scale structure of the cosmos. We see its effects, not it.
And as our sources reminded us, there are several leading theoretical candidates for what dark matter might actually be made of: WIMPs, axions, and even those primordial black holes we discussed. It's like a cosmic whodunit with a range of potential culprits, none confirmed.
Exactly. Weakly interacting massive particles, or WIMPs, are hypothetical particles that would interact through gravity and the weak nuclear force, but not electromagnetism. Axions are another class of hypothetical particles, actually proposed initially to solve a different problem in particle physics, but which also happen to be excellent dark matter candidates due to their predicted properties: very light, very weakly interacting. And then, as we've discussed, primordial black holes remain a compelling possibility, particularly if they exist within a specific mass range.
Right, and then there's this classification of dark matter as cold, warm, or hot, which is based on the theoretical velocities of its constituent particles. It seems like the cold variety is currently the most favored model.
That's generally the consensus, yes. Cold dark matter, or CDM, characterized by its relatively low particle velocities compared to the speed of light, aligns most effectively with the observed distribution of galaxies and galaxy clusters in the universe. Its slower speeds allow it to clump together gravitationally much earlier and more easily, forming the halos that are thought to provide the gravitational scaffolding for galaxy formation. Hot dark matter, moving too fast, would smooth things out too much.
Okay. So when we consider dark matter around galactic cores, the idea of those dark matter spikes around supermassive black holes fits well within the cold dark matter paradigm, right? The black hole's immense gravity would naturally attract and concentrate these slower-moving particles over cosmic time.
Precisely. And as we noted, these dense concentrations could have subtle but potentially detectable effects on things like gravitational waves from merging black holes, which scientists are actively searching for with instruments like LIGO and Virgo.
And then there's the contrasting idea of fuzzy dark matter. This concept of ultralight particles forming these diffuse, almost wave-like structures in galactic cores. That's a very different picture compared to dense clumps of WIMPs, isn't it?
It is. This model is motivated in part by observations of some galaxies that appear to have less dense central regions, smoother cores than predicted by standard cold dark matter simulations. The wave-like nature of these extremely ultralight particles, behaving more like waves than particles on galactic scales, could potentially prevent them from clumping too tightly in galactic centers, leading to these more diffuse distributions. Some even theorize they could form Bose-Einstein condensates or dark stars at the very center under certain conditions.
It's remarkable how these diverse theoretical frameworks attempt to reconcile our observations with the elusive nature of dark matter. It shows we're still exploring. And our sources also brought us back to those powerful relativistic jets emanating from near black holes. These jets are really dramatic.
Yes, absolutely. These jets are a prime example of matter being propelled to near relativistic speeds in the extreme gravitational environment right around supermassive black holes, likely powered by the accretion disk. The particles within these jets exhibit the significant relativistic mass increase and time dilation we discussed earlier. These jets are thought to play a crucial role in galactic feedback mechanisms, basically, regulating the growth of galaxies and their central black holes by expelling energy and matter back into the host galaxy.
So we have this intricate web of interconnected phenomena. Dark matter, exerting its mysterious gravitational influence, possibly clustering around supermassive black holes at galactic centers where gravity is at its most extreme, accelerating ordinary matter to near light speed, and causing all sorts of relativistic effects, including those spectacular galaxy-spanning jets. It's all happening together.
Exactly. Investigating these complex interactions, how dark matter might influence the behavior of supermassive black holes and relativistic jets, and conversely, how the extreme environment around these objects might provide clues to the nature of dark matter itself, could really be the key to unlocking some of the universe's most fundamental secrets regarding both dark matter and cosmic evolution. They're probably linked.
So to bring it full circle, this exploration began with your intriguing question about dilated matter, a concept that, while maybe not a standard physics term, has guided us through an incredible landscape. From the expansion of the universe itself to the mind-bending realm of relativity near black holes, and finally landing right in the middle of the ongoing quest to understand dark matter.
What's truly remarkable, I think, is the interconnectedness of these seemingly disparate ideas. The large-scale expansion of the cosmos, the microscopic behavior of atoms under extreme heat, the bizarre effects of relativity at high speeds and strong gravity, and the enigmatic nature of dark matter, they all somehow weave together to form our current, albeit incomplete, understanding of the universe. And those extreme environments found at galactic cores, those cosmic powerhouses, may indeed be the ultimate laboratories for unraveling some of the universe's deepest mysteries.
It really leaves you pondering, doesn't it? Could the unusual phenomena we observe at these galactic hearts, these engines of cosmic activity, actually be the crucial link we need to finally understand the true nature of dark matter, and perhaps even refine the fundamental laws that govern our entire universe? It's certainly a question to keep turning over in your mind.